I'll just say again, we were walking around with the microphone, and I guess if Gordon and Keys could use this microphone, it'll save us trying to run the microphones backwards and forwards all the time. And if you could just identify yourself and shoot ahead with the questions.
Greg Hodges with CGG. I wonder if you could go back to, I don't know about your third or fifth slide, where you showed the various types of logs and this near magical E-log. Yep. And then if one of the guys, Adrok, could explain what the E-log is. I think you said you're not sure.
No.
Yeah, this energy response.
Yes.
E-log, what is it?
I'm going to hand it over to.
Yeah, I mean, basically, it's the energy returns from the ground. So we transmit energy into the ground, and we conduct an FFT analysis of the data that comes back, and we present it as an energy log.
So is this responding to the pyrite or the gold? Because we only saw it compared to the gold assays, not to the amount of pyrite.
I'll answer that. From what we've seen in the drilling, and this is exactly what we're trying to work out. We need a little bit more drilling where we've got these scans, but it would appear, I would make the initial interpretation that it's actually seeing the galena, the lead sulfide, not the pyrite, although there is disseminated pyrite through the meter of altered granite. The solid layer that's associated with gold is really a galena-rich layer. So you could say that rather than targeting gold, we actually target galena because as galena goes up, or the lead grade goes up, the gold grade goes up simultaneously. There's probably not enough gold in there to be visible by any technique. So, I think what it's corresponding to is the amount of galena.
Okay, so it's got, if I'm reading it right from here, it's a bit blurry, or my eyes are. It's several orders of magnitude more sensitive to this thin galena than to anything else in that whole section. Is that, Gordon, is that what it is? Why is it so sensitive to galena as the conductive layer in there?
Yeah, well, I mean, the truthful answer is we don't know. I mean, this is the first time we've done a gold exploration project, and these are the results that came back. So we just provided the results to the clients, and the clients interpreted the results.
Then what's the sulfide log beside it that isn't responding to the galena or iron sulfides?
That's one of our spectral measurements. So we trained on some core samples that Simon and Citico had sent us in Scotland, and we scanned them in the lab, and we presented the sulfide hits throughout the column.
But it's not seeing the galena, which is a sulfide, or the pyrite that's with the galena.
Yeah, the main reason for that is the samples, the bulk of the samples that we got didn't have galena in, but we're still analysing the data for that. So we're still getting samples shipped over from Citigold, and we're building up the database and knowledge for that.
Doesn't make a lot of sense. The energy response is, I guess, off scale for the top 100 meters, and then it drops to a constant level. Shouldn't the energy response generally get less with depth? Further down and come back, it's going to lose energy along the way there somewhere.
Yeah. I mean, the energy log. I mean, it's our interpretation of energy. I mean, we're not measuring the dissipation of the voltage or the power in the ground. By energy, we're measuring the returns that we're getting back from the subsurface.
Which, the further down each return later should be smaller. That's what's confusing. Okay. What's the weighted mean
perhaps Case can explain that, because Case has model a bit more data than I have.
Yeah, I asked Gordon the same thing what this energy is, and he didn't tell me. But so I've never seen these results before. But what I have been doing with for Adrok at university is basically run simulations, try to figure out what these anomalies actually are. And so I'm not going to answer your question because I don't know what it is. But basically what they're doing is they're taking their return and applying a whole bunch of signal processing techniques to it, ending up with various measures which have names like energy because it has something to do with absolute value or something like that. And then look for anomalies without really trying to figure out what they are.
Okay,
and
yeah. What's the E gamma then?
I don't know. I don't
Okay.
know what it is.
Somebody there
Well,
must-
it's a parameter of reflectance. So we use a reflectance algorithm to measure the energy coming back.
Okay, because it's pretty flat except for what looks like noise. And the mean frequency, is that, what frequency was transmitted there that you're getting these back? And I would expect the mean frequency to be lower the deeper you go because, of course, the higher frequencies are more absorbed shallower. So
Yeah,
can you
the,
just
yeah, the high frequencies are getting, the higher frequencies are in the shallow section, the lower frequencies are in the deeper section.
So is every blip on the mean frequency a reflection?
Well, we don't know. I mean, it's,
Okay. Well, I don't want to hog it. I got lots more, but if anybody else wants
But
to.
does anyone have a question to let Greg water his throat again?
Can I just make a comment regarding the blips? What I should just quickly describe, because the geology I think does have a significant role to play here. There are multiple structures that this is going through, and it's really only a few of them that have the sulfides on. So those little blips there, we don't have the structural controls yet because there's just so many structures and they're in different orientations. So these may well be reflecting off other structures, but we just don't have that structural control. Even from oriented drill core, it's complicated enough that we just don't know. And I don't think we'll get to that detail yet. Okay, so there's lots and lots of cores. And we've gone through exactly these questions internally because we needed a technique, right? So we've scrutinised it pretty heavily and we've tried to match up things like E gamma, mean frequency and stuff. And at this point, we haven't been able to find anything other than this sort of magical energy log that actually corresponds to the sulfides.
Daniel Satel, EM Solutions. How do you make your conversion from time to depth? Because you're showing here a depth trace, I imagine.
So we measure depth using our WAR scans. So when we separate the transmitter and receiver, we can triangulate through the subsurface. So we can convert from time to depth that way. So we use two methods. We use a normal move-out method, which is very similar to seismic techniques, and we use a ray tracing method as well. So these are two independent techniques for measuring the depth.
But then how do you determine the velocity of your medium?
In fact, in case you've been modeling the velocity.
Yeah, so Gordon, I was actually sort of answering that, basically using a normal move-out analysis. I'm not sure if everybody's familiar with this, but if you plot a reflection as a function of offset, theoretically it's a hyperbola, and if you can find the slope of the hyperbola, you know the velocity. So that's the basic method. It's just a pretty standard method in seismic, also in GPR. There's another method that we sometimes use. It's borrowed from the velocity spectrum method in seismic. So it's similar. You basically look at correlations as function of how you warp the hyperbola, and you get some plot where you read off the velocity. Up to a certain depth, of course, you lose the triangulation because your base is too narrow. So that's one method. And if you know the material like granite here, you have a good guess of what it would be anyways. So I think that's in general how it's done.
Hi guys, my name's Jan Frank from Vancouver, Canada with International Ground Radar. I've spent the last 23 years of my life working specifically with long-range ground-penetrating radar. Unfortunately, I'm going to be asking this from the constraints of what I understand conventional physics to be. Gordon, you did actually mention on your presentation that you were working in the single-digit megahertz range on this project. Is that right? Did I hear that right? I don't remember what it was, like 3 or 7 or something.
Yeah, it's, it was between sort of 3 and 10.
3 and 10, okay, single digits. And, sorry, Simon, you were saying that, these are 300, 400, 600 meters deep, and you're picking up reflections that are on the scale of centimeters, maybe decimeters in reflectivity, in terms of the scale of these galena intercepts. Is that right?
Yes.
Okay, from a conventional physics standpoint, that's really confusing because the wavelength, let's assume a velocity of 0.1 0.12. That gives us a wavelength of about 40 meters. And what we would expect, again, from conventional physics is that the narrowest or the thinnest reflective target we could have is maybe a half or a quarter of the wavelength. So we'd need to be something on the range of about 10 to 20 meters. In a laboratory environment, there is a paper from Russia in 1996 that did speak of something that was 1/10 of the wavelength, but even then would be 4 meters thick. Your orders of magnitude thinner than that, and we're picking it up with single-digit megahertz radar. I don't understand the physics there.
All right, yeah, well, I mean, the standing wave that we send into the ground is large. So we showed that in the presentation. But within that large wave, we've got resonance frequencies within that wave. So it's acting like a carrier wave going through the ground with the resonance within that wave. So we're obviously, for thinner layers and for thinner targets, we're obviously getting reflections back from the resonance frequencies that we put into the ground.
Could I amplify that?
Yeah.
Yeah. So I've been trying to understand this too, and the only thing I can really offer is some simulations on this, where indeed what you typically describe happens if you have a reflector that's of the order of the size of the wavelength, and you get something back, and then you make it narrower and narrower, it gets weaker and weaker. But I don't know exactly how thin it can be before you lose it. So this looks. I haven't seen this before. So,
Okay.
yeah.
So, sorry, I don't want to hog the microphone, but Gordon, I do have another quick question for you. In your presentation, it was a really good presentation. You had me going, like I understood everything until you got to the word photons. Can you explain the use of the word photons? Are we talking about photons in the visible spectrum, or are you generating photons in the megahertz range, which is theoretically possible in a laboratory environment? So what was the word photon? Because it's actually in a couple of your papers, and it is in the patent as well. So are we using, I realize that photons are in the radio frequency range, of course, but are we using conventional radar, or are we using photons?
Yeah, well, I use the word photons in the context of the antennas, the antenna chamber. So inside the antenna chamber, we launch the frequencies into the chamber. We resonate the frequencies inside the chamber, and we create this lased, in inverted commas, effect. So we produce that standing wave that comes out of the end aperture. So that's the context I was using that word.
Can I amplify that too?
Sure.
Okay.
Yeah. So I've been thinking about, and I'm sure everything can be reformulated without using the word photon, because no quantum effects really appear here.
Okay.
At least not directly.
Sure, okay, so we'll take away quantum physics and we'll concentrate on conventional physics. So your antennas, I haven't seen them here, unfortunately. I was asking you if you had one here, but from the photo, they're about, what's the aperture and the pipe? 10 centimeters or something, and maybe about 1.5 meters long, is that about right?
Yeah, well, the antennas we use for City Gold that charges towers were about that sort of dimension, yeah.
Okay, and it is, in RF engineering, it is possible to make a fairly directional antenna using reflectors, but generally, I've never heard of one, and perhaps other engineers here have, that's less than about 10 wavelengths, and then you start getting some directionality. So again, if we get, back to your single-digit wavelengths, you need an aperture over 3 kilometers long, and even with your conditioning. So we can do dielectric loading, which is what you're talking about. And if you use optical glass, yeah, you're going to get a little bit of reduce, but it's not going to go from 3 kilometers down to 1 meter. And even if you did do that, it would be a highly inefficient antenna. You wouldn't get any penetration at all. So you could use ferrite loading, but then you just get a really ringy antenna. You wouldn't get anything out of it. So again, from a conventional physics standpoint, don't get it.
All right, okay.
Want me to take it?
Yeah, go for it.
No, you're right. But the aperture of the thing is certainly way too small to get a directional beam. And there was actually one plot that Gordon showed where we measured the power output as a function of angle, and there was a moderate 6 dB peak, but nothing like a beam. But the one plot, the animation that Gordon shows with the what's called the SAR plot or something. So this is actually when we have an array of 200 meter long antennas firing simultaneously. And no, that's about 10 wavelengths, just like you said. And yeah, and so that's where the beam is. It's not coming out of the individual apparatus.
Jim McNay. One of the things that I deal with a fair bit is skin depth. Have you ever done an experiment where you have your transmitter on surface and taken a receiver underground with some conductive cover between you and the receiver and had seen direct transmissions through the material as opposed to interpreting reflections at the surface?
No, we haven't done that. And the only reason we haven't done that is that we need to have a trigger cable between the transmission electronics and the receive electronics to handshake until the receiver when we're transmitting. But yeah, the case study that Case presented at the ASEG in Denver, and that was a transillumination experiment through rock underground, and we did it horizontally instead of vertically. So yes, we have done that experiment, but horizontally, but not vertically.
And was that conductive rock?
No.
Well, it was through limestone. Yeah.
That was that text point of
Peter Fulligar Geophysics. Yes, just to follow up to Jim's question, the attenuation of electromagnetic radiation is based on, or affected, or controlled mostly by conductivity. You haven't mentioned the resistivity or conductivity, but certainly it's typically related to the product of the frequency, the permeability constant, conductivity. So have you done some analysis of the conductivities of these sites? And the attenuation with distance is exponential, so for reflectivity we've got to take into account twice the predicted depth to determine what the total attenuation might be. And as already referred to, the signal is highly dispersive, so as we go deeper we're going to get less and less resolution. So again, it's very hard to understand how you can possibly get sharp reflections from very great depths.
Yeah, so not in the talks here, but in the SEC talk in Denver, I described a attempt at actually measuring the conductivity directly from attenuation. And for the limestone, the results were consistent with what corresponds to a skin depth of about 160 meters. And the conductivity, I forget the exact number, it was something like 0.7 millisiemens meter, which is consistent with dry limestone. So the hypothesis was that the stuff comes through because the limestone is actually bone dry, and perhaps the same thing happened to the granite. But I don't think there's any claim that in highly conductive environment we won't have any losses. That's my understanding of it.
I think you quoted 13,000 ohm meters for that limestone.
Yeah, it's possible. Yeah. Yeah.
Can we just make sure we use the microphone so that the punters looking at this in 2 months' time can hear the questions as well, please. Just before Mike has the mic, can I just clarify your area at Charters Towers dewatered to the depths that you're exploring to? Is it?
Part of the mine has been, but we're not going through areas that have been previously mined.
Okay, so what level is the water table?
30 metres.
Yeah. And it's presumably brackish, saline. I mean, certainly once you get out of Charters Towers, it is.
Yeah, not terribly saline. No.
Mike.
Two quick questions and one slightly more in-depth question in your hands, Mr. Chairman, as to how far I go with them. First question to Simon. You described drilling as being inaccurate and old-fashioned. Has that statement been run past JORC up to this time?
No, it hasn't. And sadly, we're constrained by the same rules and regulations as every other company that has any interest in the stock exchange. And so all of our drilling, yes, is JORC compliant, and that's how you define a reserve and resource. And the problem here is that we've got the reserves and the resources defined by previous drilling, And what we're doing here is exactly what Adrok had sort of advertised to us, is that using this as a pre-drilling type area selection tool. So rather than using drilling, which has been done in the past, when the guys first mined this area, what they did is they actually mined along the structure, and that was their historical form of drilling because they didn't have drill rigs. So it was hit and miss. And the fact that it could go for 30 years, this entire gold field for about 30 years, with companies going in and out of high grade and low grade gold zones just on. They didn't have any structural information other than the area that they were mining through. They didn't have any previous drilling. And so their exploration technique was to mine along the structure until they hit some more high grade and then mine through that and then mine along low grade until they hit more high grade. We want to avoid doing that. And certainly one of the things that's been a problem in the past 10 years, and companies such as BHP, Rio, Mount Lation, those sorts of companies have all come in here, they've all held mineral tenements over Charters Towers. They've all put drill holes in it, but they didn't understand the geology and the nature of the ore zones here. And they expected to put 1 or 2 drill holes in, or 3 or 4 drill holes in, and expect to find a high-grade hit, and then around that high-grade hit to find more and more high-grade hits, enough to sustain a large mining operation. That's not the nature of the geology, and that's the key thing, is that this, you've got to understand the nature of the ore zone before you start going and pinning holes in it. And if you drill at about at 100 metre spacing, okay, you'll miss 100,000 ounces. And for us, that's just not good enough. I don't think anybody, I think that's good enough. That's just, to say that, you're going to drill at 50 metre spacing, which is the JORC standard, it still means that we're going to miss something in the order of 50,000 ounces because the grade is so high, it's in such little pods that, we just can't afford to drill at 50 metre spacing. And John Aronsky just gave a talk, and a few people might have been there, saying that, we need to start to think about new methods and new technologies and stuff to try and reduce the amount of time and expenditure wasted on drilling and techniques that aren't getting us anywhere, and start to adopt things that are. And that's what we've tried to do. I'm not here because I work for Adrok. I'm here because this seems to work. And so what we're using, what we thought we were going to use this for, and it seems to be working, and we wanted the spectral stuff. We didn't actually want this energy. We didn't even know about the energy plot until we started seeing the correlation. So what we're going to try and do is say, okay, this energy is actually telling us where on that structure there are sulfides that we could actually drill to see what the grade is. But I'm not going to, as chief geologist, I'm not going to approve $90 million of drilling because we're drilling 500 metre deep holes through granite where we see nothing for a 1 metre intercept where we think we may or may not get gold. And so any technique to me that refines or concentrates the area where we might drill is a good thing.
Not sure whether I'm still online. I am. No one will disagree that we need to cut down on drilling. The topic in front of us is the methodology here. And the second quick question that I had was just looking at energy response. I'm just wondering what the message is for us here, that the way you've plotted that horizontal axis on energy response is you've got the low numbers on the right where you've got what you have been implying is a large energy response. Can you just fill, so this is a question for Gordon, of course. Can you just fill us in on what's your thinking there? The energy is reduced when you go through a target, is that correct?
Yes, yeah, I mean, on the left-hand side of the energy log, that's the lowest energy that's coming back, but as Simon mentioned in his presentation. And on the right-hand side, it's the high energy levels. So yeah, I mean, from this, we'd interpret that our energy is getting absorbed or sucked up by the ground at that point.
So you've got several orders of magnitude of sucking up of the energy at depth 180 odd metres, and yet there's still buckets of energy propagating down so you can get a log down to a depth of 500 metres. Am I understanding it correctly?
Yeah, I was wondering this too, and I don't know why, but I have a possible explanation, I think, and I'd like to run it by you, and feel free to shoot it down. So, so first of all, where does all this stuff come from? Well, if these are reflections, I assume, so we have granite, but it's sort of fractured and a little bit irregular, and from those irregularities, we get backscatter. So if we accept that hypothesis, then if there's all of a sudden a smooth region, then you won't get any backscatter from that smooth region except from the top and the bottom. And so you should then see a hole in your returns, whatever it is, whatever that energy is, and then it comes back up, because no, it will still go through. That's the only thing I could come up with as an explanation.
Okay, I do have a third question, Mr. Chairman.
If I could put something in before the third question, Mike. As I understand it, on that energy log, you've taken the lowest value and then reassigned it to 10 to the minus 3.
That's right.
That's
what I said
right.
at the
So
beginning.
if that, we're not talking about 2 orders of magnitude change, we're talking about a number that was being changed. So you could have, instead of taking that lowest value, you could have drawn a red line through it. And the squiggle would look like a squiggle all the way down without a big spike in it. Is that right?
Yep.
Right. Okay. Back to you, Mike.
Okay, I'm now just taking a look at this interesting article that was published in the Journal of Remote Sensing last year, and quoting from page 308 about the methodology. As the beam, this radar beam, encounters the component minerals, it stimulates the electrons of the atoms to release energy according to their compositions. So you're stimulating electrons. Now, we're getting here into the physics of spectroscopy and molecular and atomic and electron excitation. And just a couple of numbers that had me scratching my head here. If we think of infrared spectroscopy, at the long wavelength end of infrared spectroscopy, as we use in the laboratory, low end wavelengths are about 1,000 microns. That's a millimetre. So millimetre wavelength is the long wavelength end of infrared spectroscopy. And that's not mucking around with atoms or electrons. That is stimulating rotational flexure on molecules. They're the lowest frequency modes of excitation you get. They're rotational on molecules. That's with millimetre wavelengths. If you want to muck around with electrons, you go back to the concept of the hydrogen atom, the various excitation series where you knock an electron off a hydrogen atom and you can get visible light. Think of the sodium line, which we all well know, that orange line. It's got a wavelength of about 0.7 microns. We knock the electron off a sodium atom with 0.7 millimicron wavelengths. That's what we need if we're going to move electrons around. You've got to have those millimicron wavelengths. Or if you're going to flex molecules, you use millimetre wavelengths or shorter. But we don't have millimetre wavelengths or millimicron wavelengths. We have metre wavelengths here. They're metre wavelengths, or from Jan's comments, maybe 10 metres or 50 metre wavelengths. We are, with our transmitter wavelengths, we're 3 orders of magnitude away from IR spectroscopy. We're 6 orders of magnitude away from stimulating electrons in atoms. So in my tiny brain, I cannot make the mental leap of the 3 orders of magnitude, let alone the 6 orders of magnitude, to connect the radar source with what you speak of as excitation of atoms or electrons to give you the signatures which you are including in your publications.
Okay, I kind of lost the question there. It was more of a statement that you're making. But yeah, I mean, we can perhaps talk about this some other time.
I could say something about it too. You know, I got involved to basically explain how it works, determine if it works, and do some measurements to show you that it actually works, which I'm trying to do. And the article you're quoting from I had absolutely nothing to do with, and I think all your objections are 100% valid. And I think, yeah, I think those explanations attempt to sort of theorize what's going on here, but I don't think there is. It's definitely not very convincing, to say the least, as you just pointed out. But I think the session here is not so much to criticize that particular article that you quoted from, but to see if there is experimental evidence that it actually works, and if there's any physical reason that it's not possible to get low frequency radar waves to return from depth to 500 meters. And I sort of have the idea that it should be possible in selective environments such as granite and dry limestone. So I think we should sort of try to focus on that. But you're absolutely right, I think, in my opinion. It may not be.
I can see some questions up the back, Ian, so maybe we'll give everyone a chance. Dave Howard.
David Howard. For Simon, please. Yep. Leaving aside the physics of the matter and leaving aside what you call the parameter being displayed, yep, and we focus on the line, why did you choose the lowest point, which I understood an arbitrary choice because you were looking for correlations?
Yep.
And 2, what would be the, I'm not sure how to express this, how close would the other low points be to that lowest point? So if you plotted up all the low values, how would they spread in a histogram, if you like? So why did you choose the low point?
Okay, so the reason that we chose the low point is, it was, as I said at the beginning, it was mainly for visualization purposes. What we're trying to do now is with Adrok. So I'm just going to diverge from the question just a little bit. What you're looking at here is our first attempt at trying to use this with geology. And we didn't really know what we were going to be looking for in the data. We thought that we were going to get the spectral response back from Adrok, and that we would see, as someone pointed out down the front here, that we would see these anomalies associated with the sulfur, which is a perfectly reasonable thing. They fingerprint sulfur in the lab. We should see the sulfur fingerprint in the sulfide response here, but we don't. Now, when we plotted all this up in the 3D models, what we found was that and it was a sort of serendipity that we came across the fact that the lowest point, which in the spreadsheet that we've got at the moment is 0, so we give it a 0.001 value so that we can plot it amongst everything else. But what we don't have is scans that have been treated together so that we can have an absolute value that corresponds with this point here, and so that we can see whether or not that absolute value has something to do with the thickness of the sulfides or anything like that. So to try and answer your question, we don't have the absolute value for that, but we know that it's the smallest value because it was the lowest value in the series, which was 0.
It was undetectable? There was no doubt?
No, it's just that's not what we've got. Like, that's why we're going to have to go back to Adrok and actually get those values so that we can plot up the absolute values relative to one another.
There was a question on the back left somewhere.
Peter Kowalczyk. I'm a consulting geophysicist. I have to express, I would say, great skepticism. But there are a couple of things that puzzle me. One is the beam is not a tightly focused beam, and you've shown that with the radiation pattern. So I don't understand why you don't see sideswipe from that structure. I would expect the reflection to come from a spherical surface as the beam propagates, and I would have expected it much earlier than you've actually shown it, because you've shown it where the structure's known to be directly below the transmitter and not at a distance that would be the nearest approach of the structure to the transmitter.
I had the same question. So,
Yeah.
do you understand that? You've got a spherical wavefront moving into the ground. Surely it's going to hit the quartz vein further up dip than directly below the plot point.
Yeah, okay. All right, I'll first approach that with what we've done from a geospatial point of view. In terms of where we've put the scan and where we know the structure is, you'll see that as we scroll through here, I put this here that the errors were always down the bottom so that we actually see the difference between what was the anomaly in the energy log and what the actual intercept was. And if you say that it should be higher up, then it may well be. What we're looking at, we don't have, except in some of the drill holes, I'm not 100% convinced that the actual elevation of the collar of the ADR scan is precise. We're trying to fit it to a pretty imprecise surface topography data set. And so we just stitch it to that. And so there will be, in Adrok's defence, there will be a bit of error on our behalf in the depth estimate. And so in some cases it might be up or down, but it's not going to be 5 metres. And what we've noticed is that it is pretty much consistently, the anomaly is consistently deeper than where we would expect it. Why that is, I don't know, but that's what we are seeing. It always seems to be deeper rather than shallower, as you might suggest. So that's still something that I think that's probably open.
I think you missed my point. This structure dips, I think, about 40 degrees. Is that correct?
Yes, yep, that's right.
So if you look 60 degrees to the left and the structure's coming down to you, that's going to be the closest point of the structure, and it's going to be a lot closer. I don't know, it'll be maybe 6/10 of the distance it is directly below you. So I would expect the reflections to come much earlier than they have come.
Yeah, look, yeah, I think for that, as I said, I think we're, I don't fully understand the physics behind it, so I'm not going to comment from a physics perspective, but I don't know why it's coming out deeper or why it doesn't come out shallower, but I think the fact that the anomaly is there is something that's got to be explained rather than why or where it is exactly. I think the first thing is to explain exactly why we're seeing a peak in the energy, because, and this is for everybody's benefit, but this was the conclusion slide, and I just want to just quickly show you through. There are a couple of other scans that we do have, and again, we've got the same thing. So this, in essence, from my perspective, and I'm someone that needs to use this information because I'm going to spend a lot of money trying to prove it, and so what I'm saying here is that there is an anomaly, and we're at the point now where I think I would believe that anomaly is there, and that we would actually spend the money to go and drill it, and that's a pretty serious commitment to prove whether or not the drill hole is actually there. But there are certainly more examples of this, and I find it hard to believe that it's just chance at this point that it's doing that, but it's up to those guys to explain.
Yeah, I had never seen this before I came here, so I think you're absolutely right. So the only thing I can think of is that somehow the velocity model was also made neglecting this, and there's an error in the velocity model and compensate each other exactly. It's the only thing I can think of.
Regis?
Hi, Regis Neroni, FMG. Thanks for the talk, really inspiring. Just a quick question. The transmitter has a pipe shape because you need a resonance chamber to focus the beam. I understand that. It makes perfect sense. I was wondering, why does the receiver has to have the same shape? Why is it a tube shape? And exactly what sensor are you using in the receiver end of the method?
Yeah, well, the sets of antennas that we use for this project, we deliberately used a matched transmitter with a matched receiver. So, I mean, they're exactly the same antennas we're using.
It's beer time, so and I'm sure these guys have got dry throats. I guess I'd like to thank everyone for coming, and particularly thank Gordon, Keys and Simon for standing up and answering those questions. That was good.